So we've now got the last four of the section. David.
Okay, thank you. Thanks for being here. Thanks to the organizers. Okay, pattern runs on matter. The free monad as a module of the cofree comonad. So I always start with this very like metaphysicsy thing because that's what motivated me the entire time. It's what's going on with this and why is math being created at all and why does the universe blah 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 blah. So what are we? Well, let's just talk naively. In some sense, we're material. I have a body, right? And in some chemical process, and in some sense, I'm something. Things are occurring on that body. I have beliefs, I have habits, and know-how. Where someone says something to me, I'm running a script right now with this talk, right? Something's running, and it'll stop. And when someone says turn on the stove and put a pan on it and stuff, these are little scripts that I can run, and the scripts somehow run on the matter. Okay, so that's what we're talking about here. Computers also, they're material things, but they're running scripts. Or our cells, they're material things, but they're running protein production scripts, etc. So whether you think matter and pattern are the right words here for this, that's up for debate. But what I'm trying to talk about is a straightforward math idea, basically that free monads differ from but interact with cofree comonads, and that I want to let you intuit this both formally and see why it might be useful. So here's 4 examples. Sorry, I forgot to mention this is joint with Sophie Libkind. And these are 4 examples that we think are examples of pattern running on matter, that interviews run on people. You can't have interviews without people running out. Yeah. that programs run on operating systems, that voting schemes run on voters, and that games run on players. Finite things happening on things that go on. So we'll explain those in our paper if you're interested in those examples. I'll kind of talk about this programs one briefly or something. But the main point is this module structure that the cofree comonad on P and the free monad on Q tensor together and map to the free monad on P tensor Q. And so that is a module in a sense I'll explain. So I love polynomial functors because it hits a sweet spot of elementary, expressive, and elegant. It's elementary in that if you want to, you can just think of sets and functions. All day long you're just doing sets and functions, nothing difficult at all. By the way, polynomial functors and containers are the same thing. It's not only elementary, it's also expressive. So the whole categorical databases story and data proc functors between them are comonoids in poly and the bicomodules between. Dynamical systems that you put in wiring diagrams, etc., and programming language theory. All of these things can be very nicely expressed using polynomial functors. And it's elegant in that it has tons of just very standard monoidal structure, infinitely many monoidal closed structures, that sort of thing. Like it's hard to think of a category with 2 monoidal closed structures, but this one has infinitely many. So it's got a lot of weird surprises. If you don't know what a polynomial functor is, all it is a functor from set to set that is a coproduct of representable functors. If you like it better to say it's a functor that preserves connected limits, that's fine too, whichever one you prefer. And a map of polynomial functors is just a natural transformation. But because of the innate lemma, because it's a coproduct of representables, and the coproduct has universal property, and everything's representables have a nice mapping out property, a map between polynomial functors unwinds into what looks more complicated there than natural transformation, but it just says for all I pick a J and for all B pick an A. And so it's the IJ goes forward in the alphabetical direction and the BA goes backwards in the alphabetical direction. But the point is that you can just go functions from sets to sets, basically in 2 contravariant ways. So it has tons of structure. All I'm really going to use today, it has coproducts and products, which I used to even talk about it at all. But there's another distributive monoidal closed structure. I said there are infinitely many. Here's one of them that's called tensor or Dirichlet product. Neil used the same structure in his talk, which has a monoidal closure. And there's a 4th monoidal structure called composition. And I use a little triangle symbol. I'll explain it in a minute. So machines, I'm going to be talking a little bit about more annealing machines today. I decided to skip the wiring diagrams part for time. But machines of type AB input lists of A's and produce lists of B's. So imagine a machine that could take a list of A's, and as you give it to it, it starts producing B's. What is a Moore machine or a Mealy machine? It has a set of states, S, just a set. And a Moore machine is a map that takes an element of S and outputs a B, and then listens for an A and uses it to update its S. A Mealy machine is a function that takes a state S, listens for an A, and uses that A to output a B and a new state. They're slightly different there, but they're both polynomial functors. So for any polynomial P, a P machine is just what's called a coalgebra of a set and a map from S to P of S. Now, when P is the polynomial B times Y to the A, I'll explain the notation a little bit. These give Moore machines, and when P is B to the A, Y to the A, these give Mealy machines. I'm not going to talk about wiring diagrams. Tensor product, which you would use to make a wiring diagram like that, has a monoidal closure, and the Mealy machines are the universal other. They're the dual. They're the Homs into the monoidal unit of Moore machines. So if you had a Moore machine in a box in a closed world with something else, the universal other thing it could be is the Mealy machine. So that's kind of how they relate. So polynomial functors, there's lots of different ways to represent them. This one looks like a polynomial. This one is a bundle. This came up in various people's talk. And this looks like a corolla for like a bunch of little teeny trees. And these are representing the same thing. Basically down here, if you apply this polynomial to 1, you get 1 plus 3 plus 2 is 6. And those are the 6 dots and the 6 dots here. And above every dot is some number of directions or elements of the fiber. And that's 2, 1, 1, 1, and 0, 0. So that 2 there represents y to the power 0. It's the coproduct of y to the 0 with y to the 0. Okay, so composite of polynomial functors is again polynomial. It's given in the usual way, like y squared composed y plus 1 is y plus 1 squared, y squared plus 2y plus 1. And here's an example of that. So if you took p of q, what you do is you write, how you get it is you take all of the ways of putting the q-ish things on top of the p-ish things. And so that triangle shape, I like for non-symmetric monoidal products, I like non-symmetric symbols because they let you reverse them easily and they're kind of nice. So that triangle represents kind of trees moving up, trees growing upward. And so you can kind of count there. It's y to the 6th plus y cubed plus y cubed plus y to the 0 plus y cubed plus y to the 0. If you count how many leaves there are, 6, 3, 3, 0, 2, 0, and that's the composite, y to the 6th plus 3y cubed plus 2. So that's this kind of trees growing up picture, and you kind of are going to need that for the free monad and cofree comonad. To understand them, they are going to be trees. So any questions about how the trees work? These corolla forests, they kind of nest on top of each other. Great, so what's a monad? So y tri, this triangle symbol, is composing. And so that's a monoidal structure on poly. And so a monoid for that would be a monad. It's a map from y to some polynomial, and a map from that polynomial compose itself to itself. And a comonoid is mapped from some polynomial to y, and a map from that polynomial to itself compose itself. And so since triangle is composition of functors, even though we think of polynomials as objects in a category, they're objects in a category, as functors, these would be monads instead of just monoids. So these are monoids in poly with this structure. They're monads on set. So a polynomial monad is a variant of an operad, a one object multi-category. So we'll be interested in free monads, which are kind of like flowchart languages. These are, imagine you have some flowchart, like, you know, are you happy or sad? And then you like pick your directions, like what's your favorite color? And you kind of move through. The language of those flowcharts would be this flowchart should finish in finite time. Otherwise, you're not going to be happy using the flowchart. Those will be like free monads, elements of the free monad. And a polynomial comonad turns out to be exactly the same thing as a category, not just a variant of, but literally a category. And that's kind of the basis for, and so like the comodules between them would be the Pla functors that, or Pra queries that Emilio talked about. But we're not going to go into that today. We're just going to talk about cofree comonads, which are special. They're not flowchart languages, they're the machines. So these are going to be more like the matter, and these are going to be more like the pattern. So the free monad, to build the free monad, so you could either read Kelly's paper on free monoids, or you could read Schulman's wonderful condensation of it on NLab, but still you're going to be working super hard compared to what you have to for polynomial functors. They're actually quite easy. So the free monad on them. So what do? You have a polynomial functor P, and you say, I'm going to define P sub 0 to be just y, the monoidal unit. And I'm going to define P sub I plus 1 to be y plus P composed the previous. And so what this does is it's going to just build trees, but I'll show that in a minute. I just want to show the formal stuff for a second. And there's a map from P sub I to P sub I plus 1 that includes y into y plus P at the base case. And then when you have the map from P sub I to P sub I plus 1, then y plus P composed Pi to y plus P composed Pi plus 1 is just given inductively. And now you define P sub infinity, P sub omega, to be the colimit of all these Pi's. So y maps into y plus P, which maps into y plus P composed y plus P, et cetera, and you take the colimit of that. And when P is finitary, like when all those little trees only have finitely many branches, then you're done. That is the free monad. And when P is kappa small, in other words, they have less than, aleph 1 many branches, then you're going to need a few directed colimits along the way. You just kind of, every time you hit a limit ordinal, you just take a colimit, and it's very simple. And now you just take the colimit of all of those things. And that's the free monad. The free comonad is almost the same sort of thing. So P super 0 will be y, P super I plus 1 will be y times P composed Pi. And again, you can project out to the y, and you can define things inductively. And then you define CP, the cofree comonad, to be the limit of that sequence, y from y times P, from y times P composed y times P, et cetera, et cetera. And unlike M, you can stop there. You don't need any higher ordinals. As soon as you've done this, infinite limit here, this directed limit, you're done. If you remember P machines, like Mealy machines and Moore machines, they have these different polynomials. A position of C sub P will be an initialized P machine. So it's like a co-algebra where you picked an initial state up to behavioral equivalence. You don't care if two states act exactly the same way in terms of their observable behavior, then they are the same as an element or position in CP. By the way, CP, its position, CP of 1, is the terminal co-algebra, if you like those words. So M, the free monad of 0 gives you the initial algebra. The cofree comonad of 1 gives you the terminal co-algebra. So if you like initial algebras and terminal co-algebras, I tend to think that the free monad and terminal and cofree comonad are kind of better concepts because you can recover the other ones from it, but not vice versa as easy. So these things are pretty different seeming, and yet they both have this y plus versus times P composed the old one. How similar are they? How different are they? Basically, one way to see it is they both have a tree representation. They're both polynomials. And so what I want to define is something called a P tree. A P tree for a polynomial P will be a rooted tree where every node in that tree is labeled by a position in P and then branches accordingly. So let's say your polynomial was y squared plus y cubed plus 1. But every time I see a y squared, I'm going to write an A. And every time I see a y cubed, I'm going to write a B. Writing this is a brilliant, I don't know who invented this. I feel like I saw it from Andrea Chensky. I don't know. This idea of labeling, maybe it's super old and everyone knows it but me, but like taking a one element set and multiplying it by something as a way of labeling is just a very convenient, cool trick. So, the pictures of a free monad are going to be trees that don't all, like they're not, they can have different depths at different points or different heights at different places. And this would be an example of an element of the free monad or a position in the free monad. This would be for the cofree comonad, they keep going up and up and up forever. Now, whenever they hit a C, no matter whether you're in the free monad or the cofree comonad, whenever you hit a C, you stop because there's no branches here. It's y to the power of 0, so there's no branches. But for the free monad, you have to stop at some point. Every one of these flowcharts ends. Whereas over here, you keep going and going unless you happen to, for some reason, hit all C's. So the pictures are quite similar in some ways. They're both P trees, but these end and these don't. Oh, I forgot to say what the directions are. So what are the directions on this thing? The directions are just the open leaves. So there's 1, 2, 3, 4, 5 of them. Whereas on this one, the directions are every single node. So quite different. As a polynomial, when I say positions and directions, I mean the elements of P of 1 versus the exponent there of the representable. Anyway, so this thing, the directions are quite different between these two things. So these are kind of very similar. The free monad and cofree comonad, they're like lists and streams, for example. They're so similar and yet so different. What else do we know about them? First of all, the free monad is a functor from poly to poly, and that thing is itself a monad. That's why it could be called the free monad. So that means that for every P, there's a map from P to the free monad on P, and there's a map from the free monad and the free monad of P to the free monad on P. And a polynomial monad is just anything that is an algebra of this monad. And the cofree comonad is a comonad on poly. So there's the cofree comonad. It takes every polynomial P to the cofree comonad on P. Right. So there's various interactions between free monads and cofree comonads. One is that the cofree comonad just interacts with itself, and that is laxmonoidal. There's a map from C cofree on P to cofree on P prime to cofree on P tensor P prime. But the free monad is not laxmonoidal for tensor. It's laxmonoidal for some other monadal products, but not for tensor. So that's not so interesting for now, but one thing I want to say is that because C is laxmonoidal, it makes sense to say to say that something is a module over it. And so this is the NLab definition of, if you look up module over a monadal functor, that's what I mean by module here. So there's a natural map that takes the element of that cofree comonad, that infinitely branching tree that goes on forever, not infinitely branching, that tree that goes on forever of shape P, and that a free monad MQ that kind of stops at some point and gives you a free element of the free monad on P tensor Q. And then you just check two diagrams, like if you take two different C-ish things, you can combine them into one and then use your phi map, or you can hit the phi map and then the other phi map, and those should equal each other. So how do you use it? Well, think of an element of CP as a tree is like a machine that's going to run forever. It's just listening for inputs and then giving outputs, a REPL, if you know what that is. Like it prints something in the terminal, you type in something, it reads it, changes states, and prints something in the terminal, and just keeps going forever and ever. So it's like an operating system. It's more like the matter part of that dichotomy. And an element of MQ of one would be a terminating program. It'll be a finite flowchart, okay? And so what happens when you do this thing? You take your operating system, you take your script, and you get something here. What happens is you lay the tree T next to the tree U, and you move forward through them both in tandem. What do I mean? The root of the tandem thing is the pair of roots, and a branch of the tandem thing is a pair of branches. So you just keep branching according to P and Q. What do you put there? You put whatever was there on P, and whatever was the P thing, and whatever was there in U. What is a leaf? Whenever your terminating thing hits a leaf, you hit a leaf. You stop right there, and you just return the remainder of your infinite tree T. So when I said before, what's a Moore machine? I said an A-B Moore machine sends A lists to B lists. A lot of times when you hear people explain that, they're going to do an inductive thing, and they're going to leave the world of coalgebras, and they're going to start writing some equations that look like they're talking to a much younger student. What happened? Why couldn't they stay where they were? The way to let them stay where they were is to use this thing here. So a Moore machine, since an initialized A-B Moore machine is a position in this cofree thing. So that's your machine, and an A list is a position in the free monad on AY. So the free monad on AY is list A of Y times Y. So there's a map from BY to the A tensor AY, a polynomial map. That's just BAY to the A, and then you can kind of cancel this out. There's a polynomial map to BY. You just kind of have to believe me if you can't read it right now. And so you can get from your machine and your list, you can apply the phi map, put them together, run the list against the machine, and then get your B list. So this is a way that you don't have to leave the land of coalgebras to talk about how a Moore machine runs the list. Okay, so programs run on operators. Here's a guessing game. You input max guesses and a goal. If they're out of guesses, you return false, they lost. And if you read in a guess, which is a natural number, if the guess equals the goal, return true. And if it doesn't, return the guessing game with the same goal, but with one less guess. And the way you get this thing is you define this polynomial, which is the sum over max guesses, which is a natural number, and goals, which is a natural number of a thing that receives a Boolean, did you win or lose? And you define a map from R to the natural numbers that plays this game. Basically, a position in my to the n. What is, I guess, I have probably no time to say this. My to the n, sorry, the free monad on y to the n is a branching tree that at every moment accepts a guess and then moves possibly to a new branching tree or stops. So it says, what's your guess? At 1, it's like, stop there. At 2, it's like new branching tree, like natural number, many branches. Maybe I should drop, maybe I shouldn't. And so this program right here is actually just a polynomial map from this R thing to branching trees. Basically, if your number of guesses is 0, you have the empty tree. And if your number of guesses is more than 0, you basically ask for a guess, which is a natural number branching. And then if that branch equals the goal, you stop and return true. You come back to R with true. And if it is not the right answer, then you repeat this story with one fewer guess. You might have another branching tree forever. Anyway, so a position sigma is some big stream of natural numbers. It's the thing inputting guesses. Maybe it's the operating system. Maybe it's you're operating this game. And then since y to the naturals and natural to y are dual, one is kind of the universal other for the other. You can kind of use what we've done so far. You use your stream of guesses and your program to get a map from R to the natural numbers times y. What this is going to do is take your max guesses and your goal, run it with the operator who's giving the guesses, and give the natural number of moves that happen until they either win or lose, and return back to R the Boolean of whether they won or lost. So that's what this machine would do. It kind of uses, so now we've seen 2 different examples of how to use this phi map. One, just in this thing, how to use more machines, turn lists to lists, and here how to run some guessing game. So in conclusion, one might be interested in what's going on with pattern and matter, whether you like those terms or not. We're thinking of patterns as terminating programs, little scripts you can run. We're thinking of matter as the dynamics of something that kind of persists, a machine. And what does it mean to run pattern on matter? So one way to think of it is to think of these scripts as a monad and matter as comonad. And then we've constructed the cofree or free monad or comonad on any polynomial P and showed how they look like 2 different types of P tree. And there's lots of different interactions between CP and MP. Many I didn't talk about today. But one thing is that matter can run on matter in this sense. There is Laxmanoidal functor from CP tensor CP to CP tensor P. So you can run 2 material things with each other and get another material thing. Pattern does not run on pure pattern in that sense. There is no Laxmanoidal structure on MP, but M is a C module. So this is what we mean by pattern runs on matter. So that's it. Thank you.
Thank you. Any questions?
Is there a dynam version of this that did like continuous time dynamics? This seems very
Continuous
like
time dynamics, it's hard to define. It can do so much. It's very polynomial in a lot of ways, except there's no composition or substitution operator that I've heard of.
okay.
So yeah.
You can't get like, because when I hear this, how to run the like
If I could
control
move to
theory
continuous
stuff.
world and still keep my try thing, I'd be like there. But because I love this composition so much, I can't quite escape the finite
state machine.
state machine. And one way to do that was with something that Kevin Arland or Kevin Carlson is and I are, but that's future work. Yeah.
So my question is about mixed distributive laws at 2 different levels. Firstly, at the level of monads and comonads in this setting, whether we get something interesting there. And then secondly, the free and co-free constructions also you said give examples of monads and comonads. And do you get something interesting there if you look at it?
Sorry, give you.
So mixed distributive laws either at the level of your
Yeah.
polynomial monads and comonads,
Yeah.
or at the level of these free and co-free constructions interacting with one another.
Yeah, so given any map from P composed Q to Q composed P, I can get a distributive law from free monad P composed cofree comonad Q to cofree comonad Q composed free monad P. So there's a mixed distributive law between P and Q.
Right.
That's one answer. I'm not sure of other answers. I don't know if that answered both of your questions simultaneously or only one of them.
The first one, so the free constructions, do they also interact nicely with them? Like if I first take the free monad and then take the free comonad, or the
I
other way?
don't know. I would love to know. Yeah, yeah. I think I thought about that and I didn't directly, but maybe there are things I didn't see. Yeah.
Okay, cool, thanks.
Yeah,
Okay, so sadly, I think, my matter, for instance, probably isn't gonna continue in this recognizable form forever.
Right. Maybe,
Um,
yeah.
So
Oh, your matter even.
when you have the model of matter as, continues forever, is it that it could continue forever, so it could conceivably stop? Like,
The matter itself, the cofree comonad, if it hits at all points in the tree, it has no options left. It can no longer receive for some reason, then it would stop. But in general, they would just keep going forever. Yeah.
The way you just described it sounds like it backs up in the tree. If it
Oh.
hits a leaf, no, if it hits a leaf, it's dead.
It's this infinitely branching tree.
Uh,
Maybe you are like some path through this tree. The only way, and if you could hit a place where you have zero options. You don't have even the option to just listen to the hum of existence forever. You get no options, then you would stop.
yeah.
I'm curious about this comment that you made at the end about
Yeah.
matter running on matter. Should I think of that as like an emergent system sort of thing where like proteins run on chemistry and cells runs on proteins, and so like there's levels that contain other levels, or is it more like two things at the same level that are interacting?
More like two things at the same level.
Yeah, Tim?
You mentioned this duality between more and meaning machines a few times. Was that just so you got a P and a Q that you could compose together like a closed thing, or is there more going on?
For any more machine,
Yeah,
I think of it as the interface as AY to the B.
yeah.
Inner hom from that to Y is the Mealy machine that, okay.
No, but
That you're-
is it, were you using that just as an example to get a P and a Q that you could tensor together in your little subscript here?
Yeah.
And then,
Yeah,
so
these
that's-
are both the sort of thing where you could take the cofree on them, which is a Mealy machine or more machine up to behavioral equivalence. And give it a list. You could use this to get the output list,
Okay,
for example, but yeah.
okay.
Sam?
Yeah, thanks. In algebraic effects, people talk about co-models and runners, and they use some of the same words as what you're talking about. Have you thought about the connections there?
Yeah, there's a very tight connection with stuff from Tarmo and
Oh, so
these people. It's almost, I think it's basically they like a choose style where they kind of take CP tensor MQ to R or something like that. This is just it turns out that very, very similar result. Maybe it's the same. But in not in the choose style, in the module style. So I think that the diagrams we want to prove we want to consider are different, but they may be the same.
Maybe time for one more question?
Or equivalent.
So when you talked about putting the two corollas in tandem and then progressing, like what?
Yeah.
So what does that? I understand that that's like a metaphor for running. But what does that correspond to? Is that the module action?
That's the module action. Yep. Is that your whole question? Yeah. Did I answer it or do you want me to?
Yeah. Like if you take 5 steps up both trees, that's
Yeah. So this little tree here could be running next to that other tree.
Yeah.
And what you do is like you have A comma A as the root. It would branch 4 different times, 2 times 2. And then the result would be BB, BA, AB, and AA, I guess. And you keep going, but once you hit these leaves, you would also make a leaf for this tensor thing. Right. This one is ready to keep, this one would end in a leaf, this one would say, aha, you left me off. The operating system would say, you left me off in this state. Yep.
One more then.
So you showed that that there was this co-module structure, but you only used the lax functor structure of the cofree component. But the monad, but NP and CP are monads and comonads respectively. And the tensor that C is latched with respect to is duoidal with the composition of which they are monoids and comonads.
Yes, right.
Do the structures interact?
In,
The module structure.
we couldn't do it if they
and
weren't.
comonad structure. Oh, okay.
yeah, that duality that you're talking about is what is important in all this.
Okay, thank you very much, David.